So hello everyone. Today we have a master seminar of Guy Nevo. Guy was born in Israel but lived in Canada until the age of 25, and he has a BSc in mechanical engineering from the University of Calgary. And he'll be talking to us today about hardware in the loop simulation testbed of a low-cost research missile. Go ahead, Guy.
Okay. So everyone can see my screen? Good. Okay, so welcome everybody. Today we are going to be talking about the hardware in the loop simulation testbed that was created for a low-cost research missile. My name is Guy Nevo, and my advisors are Professor Tal Shima and Dr. Oded Golan. So in this seminar, we're going to be discussing the motivation behind this project. We're going to be giving a short overview of the Cornetto project, which is an example project that we're testing the testbed on. We'll give an overview on the hardware in the loop in general, discuss the components that make up the testbed, and then at the end show a demo, discuss results, and just a quick summary and suggestions for future improvements. Okay, so let's begin with the motivation. So what we're trying to do is to create a hybrid simulation for validating guidance, navigation, and control algorithms from inside the lab for a low-cost research missile. And so what we're trying to do is to combine physical components with mathematical models. So physical components would be such as those of the missile, so flight computer, servos, etc. And the mathematical models would be the flight dynamic model and the virtual IMU and other components that we will be discussing in just a moment. And like I said, we're testing this testbed with the Cornetto project. So a quick overview on that. So what is the Cornetto project? It is a project to design and build a low-cost research missile that's going to be reusable for testing, again, guidance, navigation, and control algorithms. The project is in collaboration with the Technical University of Munich in Germany. And so the Technion team consists of undergraduate aerospace students in their final year and a few master's students such as myself. So a quick overview of the physical layout of the missile. So at the very front, there's going to be a seeker. I say that there is going to be one because as of now, we're not testing any guidance algorithms, and so there isn't a seeker yet. Behind this, there's the avionics section. So that's where the flight control computer goes, the GPS, battery, power distribution, and the rest of the electronic components. Behind this, there's the parachute, which is in the recovery section of the missile. And this parachute is what makes the missile reusable. And further back, there's the wings. There are 4 wings. And these are mainly just there to increase the range of the missile. And at the very back, that's where the motor assembly is. So this includes the actual motor as well as the 4 fins that are used to steer the missiles. And each fin is connected to a servo, and that's how we generate the fin deflections. Overall dimension of the missile, it's about 1.1 meters tall and with a 90 millimeter diameter. So it's quite a small missile. Okay, so now we're going to be discussing the hardware in the loop. So a quick overview on that. So the purpose of the hardware in the loop simulation is to validate the design of the GNC algorithms using physical components in real-time simulation. So the overview is as follows. We have a flight computer, we have a simulation computer which runs the flight dynamic model, which uses the fin commands to calculate the full state vector of the missile. Part of this is the attitude. The attitude is being sent as a command to the flight table, which generates the rotations that the missile would experience in flight. And inside the flight table, there is an IMU. In our case, it's a part of the flight control computer, which is a PICSOC. And then the IMU is going to measure the rates and calculate fin commands by running the GNC algorithms. I'm going to also mention the hybrid IMU that's going to be implemented. The reason for that is that the flight table only generates rotational movements, but it cannot generate linear accelerations. And so the PICSOC needs to have some sort of a hybrid IMU that combines the physical gyro readings with virtual accelerometer readings from a virtual IMU, which is running on the simulation computer. So like I said, it generates fin commands, which are sent to the servos. The servos are being measured by optical encoders, and these are sent to the flight computer to close the loop. So now we're going to go into depth of each component, starting with the flight control computer, or FCC for short. So the model we're using is the MRO PICSOC flight computer, also known as the PICSOC-1. What we like about it is that it has built-in sensors. So it includes a 6-axis IMU, which means a 3-axis accelerometer and a 3-axis gyroscope, as well as a magnetometer and a barometer. The software for the PICSOC, we're not using the software that it comes with. Instead, we're flashing our own software that was designed using Simulink. The way we interface it with the rest of the testbed, so for communication over serial, we have serial communication over USB, and we are interfacing with the servos directly. We have PWM ports that send signals to the servos. This is an off-the-shelf component, so it's quite easy to get our hands on, and if we need more, we can get more. And a nice feature about this particular unit is that it has 4 mounting holes once you remove the outer cover, which is used to have a secure connection attachment to the flight table. So the software that we're using is custom made. So this is the software I designed. What you can't see here is the block for a serial input. So it receives input from the simulation computer through the serial input, and then sends data back over serial to the simulation computer over here. And this entire block gets flashed onto the PICSOC, and it operates at 100 Hertz. The other input of the PICSOC is the gyros right here. So this interfaces with the physical gyros and measures them. And so it works as follows. So from the simulation computer, we receive the heartbeat, which we're going to discuss in just a minute, as well as autopilot commands, the true state vector of the missile from the flight dynamic model, as well as the virtual IMU data, and a few flags that are going to control the different modes that the PICSOC can operate at. So for example, there's the IMU merge block. And so what it does is we can enable the real gyros flag in the initialization script. And then we would have a hybrid IMU that takes the physical gyros measurement and the virtual accelerometer measurements to be used by the rest of the algorithms. Or if this flag is set to false, we would be using only the virtual IMU data, so virtual accelerometer and virtual gyroscopes. Similarly, the inertial navigation system, or INS for short, we can either use the IMU measurements to estimate the state vector for the missile, or by disabling this flag, we can use the flight dynamic model true state vector directly. So the attitude commands, inertial navigation system data and IMU data are being sent to the autopilot, which calculates attitude commands, which are then translated into fin commands, and then this goes into the servos. So also, we are sending back information over serial to the simulation computer, including the fin deflections. So that's in case we want to use virtual servos rather than physical servos. And also some other information for mainly for debugging, including the heartbeat. So what is this heartbeat? Essentially, it's just a discrete counter that's generated on the simulation computer. And so the simulation computer sends this value with every message to the PICSOC, and then it receives this value back with a response from the PICSOC, and we can use it to measure the delay in communication for a round-trip signal. And so on average, we measure a delay of roughly 15 milliseconds, at most 20 milliseconds. Excuse me. So the way we integrate the PICSOC with the rest of the simulation is as follows. So the PICSOC is mounted into the innermost gimbal of the flight table. It has its IMU built in. Power and communication happens over a USB cable, which gets routed through the slip rings of the flight table. And similarly, the servos get their commands from the PWM outputs, and these are also routed through the slip rings of the flight table. And the PICSOC attaches with a custom-made bracket that I designed in SolidWorks and 3D printed. So that sums it up for the flight control computer. So now we're going to be discussing the servos and the encoder assembly. So in flight, the missile is steered with the 4 fins at the back, and the servos are going to be moving them, and the servos are operating in open loop. So what this means is that we send the servos some command, and the fins are going to, the servo is going to track these commands, but we don't know what the actual positions of the fins are at every given time. In the lab, however, we do not generate aerodynamic forces with the fins, and so we need a different way to calculate these forces and moments. And so we do that with the flight dynamic model. And so we need to measure the fin deflections directly in order to send them to the flight model. So the servos we're using in the testbed, they are the same servos that are used in the Cornetto project. So these are the SV1232 MG servo from Savox. They are quite high power, and they are small form factor. The encoders that we're using to measure the fin deflections are these encoders from UMO. What's important to note is that they are incremental and optical. So optical just refers to the sensing technology that's being used to measure the angle. Incremental means that every time we supply power to the encoder, the current angular position is considered 0, and from now on we're tracking the angle relative to this 0 position, as opposed to an absolute encoder, which gives you the angle with reference to some physical point on the sensor itself. Also, the resolution of this encoder is 1024 pulses per revolution, which translates to an accuracy of about 0.09 degrees, which is a more higher resolution than the servos themselves, so it's not a bottleneck. And I just want to stress the fact that these encoders are not used in the Cornetto missile. They are only used in our test bed because we need some way to measure fin deflections in the lab. So the way we connect these servos and encoders are with, again, a custom housing that I created in SolidWorks and 3D printed. There's also a fin. So this fin is here just for visualization so that the user can see the fins move. And everything is connected with the servo and the encoder are connected together with a rubber coupling. And as far as the wiring goes, so the servos receive the signal from the PICSOC, but the PICSOC cannot supply power. So instead, what we're using is a dedicated power supply unit over here. You can see it, and this is what powers the servos. And the encoders are connecting directly to a National Instruments data acquisition card that's installed on the simulation computer. And this way, the simulation has direct access to the measurements of the encoders. Okay, the next thing we want to do is identify the transfer function for the servos. There are 2 reasons why we want to do this. First of all, we want to be able to have an offline simulation and we need to know what these servos are going to behave like. That's the first reason. The second reason is that for designing the autopilot algorithms, it's quite useful to have these transfer functions. And so the way we're going to identify the plant is using the fast Fourier transform method, and so FFT for short. And so what we do is we supply a chirp input signal. Some people call it a sine sweep signal, with a 3-degree amplitude, and frequency ranges from 0 to 50 hertz. The reason for this range of frequencies is because we want to be able to see the drop-off in gain and phase. And 3-degree amplitude is a good balance, where it's high enough that we can measure it accurately, and low enough so that we are not hitting the limit for the speed of the servos. Because once we hit the speed limit of the servo, the system is no longer linear, and a transfer function, we cannot find a transfer function for a nonlinear system. So once we put in the input and measure the output, we can compute the FFT, the fast Fourier transform, which gives us magnitude and phase information, which we can plot as a sort of a Bode plot. And from this, we can estimate a transfer function. So we're using a second order approximation here. It's good enough for our purposes. And this is the transfer function that was estimated. And this is what we're going to use in the offline version of the simulation, as well as for designing the autopilot algorithms. Okay, so moving on, now we're going to be discussing the flight table. So this is the flight table that we're using in the lab. So what the purpose of a flight table is to reproduce the angular rates that the missile would experience in flight. And it's made up of 3 rotating frames. Each one rotates individually, independently, also called gimbals. And the pickstock sits in the very middle with the IMU, and that's what measures the rates. And the 3 gimbals define an Euler transformation. So for example, as the outermost gimbal spins, we get a yaw movement, the middle gimbal produces pitch, and the innermost gimbal a roll movement. So when I received the flight table, it was uncontrolled. So what that means is I only had access to putting in an input of voltage between -10 and 10 volts. And the output, aside from the actual angular rates, which are measured by the pickstock, the signals we can receive are the raw encoder angles. So again, these are incremental encoders, which give a relative angle, and a 0 index pulse, one for each gimbal. And so what this is used for is, if we give each gimbal a 360-degree turn, we can take note of the position of the 0 index, which is a physical position on the gimbal, and use it to convert the relative angles to absolute angles. So now we have access to absolute angles for each of the gimbals. So again, we want to make sure that the system is in fact linear before we can start creating control algorithms for it. And we do this with a pretty simple experiment. What we do is, for each gimbal, we supply a steady voltage, a few steady voltages, and we measure the steady state response, and we can plot it. And what we see is that we have a dead zone for each of the gimbals. And so what this means is that there are voltages that we can supply that result in no movement of the gimbals whatsoever. This means that the system is not linear, but it's pretty easy to overcome this issue by using what we call an augmented voltage, which is going to be the new input to the system. And all it does is we're going to add some sort of offset to the voltage if it's positive, or remove it if it's negative. And using this sort of transformation or correction, the system now behaves linearly. So now that we have a linear system, we can do the same fast Fourier transform method to identify the transfer function for each of the gimbals. And so this is what we see here. The blue line are the results from the FFT test, and the red dotted line These are the estimated transfer function. And the resulting transfer functions that are estimated are shown here below. And as expected for a brushed DC motor, the transfer function is made up of two real poles. Now you can probably see that there's some unexpected behavior over here at the end at high frequencies. The reason for that is because we have a maximum and minimum input voltage we can supply to the motors. So like I said, plus minus 10 volts. And beyond that, we have saturation such that the system is not linear. And so this is what we see here. A way around it would be usually to just decrease the amplitude of the input signal, but there's a limit to how far we can decrease it before we cannot measure the response accurately. Okay, so now we want to specify some specifications for the flight table. So starting simple, we have a 6 dB gain margin requirement, 30 degrees phase margin, also rise time, settling time, 0 steady state error. And at the bottom, we have a maximum speed limit for each of the gimbals as defined by the manufacturer specifications. What's slightly more complicated is the effect on the autopilot gain and phase. As an example, to explain this better, let's take a look at the roll autopilot. So we're going to be using a standard cascaded controller where the inner loop is on roll rate and the outer loop is on roll angle. And this is what it would look like in the air. But in the lab, we're adding a few extra blocks. So the encoder, for example, we can assume it's going to have a negligible effect on the loop, but what will not have negligible effect is the flight table. So the flight table is going to add some gain and phase to the loop, and we want to minimize it. So what we're using for specifications is as follows. At most, an effect of 1 dB and 5 degrees due to the flight table from frequency of 0 up until the bandwidth frequency of the associated autopilot. So for example, for roll, we're expecting a bandwidth of 5 Hertz. So that means up to 1 dB and 5 degrees effect up to that frequency. Okay, so we don't have time today to go over the entire controller design, but basically what it looks like is like this. So it's a cascaded controller with an inner loop on angular rate and an outer loop on angular position. The reason for this is that it allows us to add a saturation block before the inner loop input, and this way limit the speed of the gimbal. And the controllers that were found to work well are a pure gain controller for the inner loop and a lead network for the outer loop. So once we close the loops on each of the gimbals, we can now see what the results are like. And in these graphs, all we're showing is that up until the bandwidth frequency of the associated autopilot, we are within the required 1 dB, 5 degrees. So for example, in the innermost gimbal, which is associated with roll, at the 30 radians a second or 5 Hertz mark, we are seeing less than 1 dB effect and less than 5 degrees effect due to the flight table. So if you look at the middle and outer gimbals, we have two plots. And that's because the orientation of the inner gimbals will affect the moment of inertia of the outer gimbals and therefore the transient response. And so we are repeating the controller design to make sure that it works for both the lowest moment of inertia and the highest moment of inertia configurations. And when we're doing this, when we're testing one configuration, then the inner gimbals are locked physically using zip ties so that they don't move. Okay, so this is the results to a step input. So we see a fairly quick response to command in roll, and pitch and yaw, or the outer two gimbals, they are slightly slower. We also see that the moment of inertia does not have much of an effect on the middle gimbal, but on the outermost gimbal, it does have quite a bit of an effect, where the highest moment of inertia configuration adds quite a bit of settling time. But this is still within spec, so that's fine. And here we're showing the flight table's ability to track sine waves. So it can track both high amplitude, low frequency waves, or the opposite, so high frequency but low amplitude waves, and does that quite well. Okay, so now we're going to be discussing the problem of gimbal lock. So gimbal lock is one of the main issues with a 3-axis flight table. So what happens is when the middle gimbal moves to a position of plus minus 90 degrees, we lose a degree of freedom, and that's not good. And so the solution is to just avoid the problematic area entirely. And so the way we do this is by introducing an additional rotation, so such that we are tracking the attitude of the missile not with reference to, let's say, the Earth axis, but with reference to the flight table axis, which is slightly different. So what we do is, let's say that the rotation from Earth to body, that's the regular rotation matrix with phi, theta, psi. So we multiply it on the right with another rotation from flight table axis to Earth axis, and the overall effect is a rotation from flight table axis to body axis. And so now we have a direction cosine matrix from which we can extract the 3 angles. We can call them alpha, beta, and gamma, and these are the angles for each of the gimbals. So we can do this initial rotation about the y angle or the middle gimbal angle such that it starts at a position which helps us avoid gimbal lock. Now, maybe this is easier to explain with an example. So let's take, for example, the following scenario. The missile is going to start with an attitude of just 0 for theta, psi, and phi. And we're just going to have a constant roll and yaw rates, and the pitch rate is going to be following a sort of sine shape. So first it's going to pitch up and then pitch down. And so the attitude of the missile, you can see right here. And so if we just track the attitude normally using these Euler angles, so what would happen is at some point the middle gimbal would approach 90 degrees, in which case the required rates for the flight table to produce, they jump to infinity. And so obviously we cannot track this scenario this way with a flight table. However, if we start the flight table with the middle gimbal at an offset of minus 50 degrees, so a rotation about the y-axis of minus 50 degrees, now we can still track the attitude of the missile, but we are going to have different angles for the flight table gimbals, such that we are staying away from the 90-degree mark, and the rates are now obtainable. So that sums it up for the flight table. Now we're going to be discussing the hybrid simulation. So this runs on a dedicated simulation computer. It runs in Simulink desktop real-time, and this is what's responsible for combining the hardware and the virtual flight dynamic model, IMU, etc. So first, we'll discuss the initialization script. So this is where we define the missile properties and the flight scenario, as well as the flags for the different modes. So we have the flight control computer flag. If we enable this flag, we're going to be using the physical PICSOC, sending and receiving data over serial communication. If we disable the flag, we're going to actually emulate the entire functionality of the PICSOC from the simulation. Flight table, we can either enable it or disable it. Same thing with the gyros. If we enable this flag, we're going to be using the hybrid IMU. So that means physical gyros, but virtual accelerometers from the virtual IMU. And if we disable the flag, then we're not using physical gyros at all, and we're just using the virtual IMU entirely. Servos, again, we can either enable them and then measure these the deflections using the encoders, or we can disable the servos and just take the servo commands that the PICSOC calculates and pass them through the transfer function of the servos. And lastly, the inertial navigation system, we can either enable it and estimate the state vector, or disable it and use the true state vector from the flight dynamic model directly. Okay, so this is what the simulation looks like in Simulink. We're going to go into each one of these blocks in detail, starting with the attitude commands block. So this is where we define the commands for the autopilot. So right now we only have attitude commands, but later on we can also add other commands for the autopilot, such as, for example, acceleration. What's important to note here is that because we have at the beginning of the simulation the calibration process for the flight table, we need to delay these commands by the calibration time, so that we're not sending a command before the flight table is even ready to track it. Okay, so now the virtual IMU block. So what it does is it receives the true state vector from the flight dynamic model. So we're using the linear accelerations, the angular rates and the angular accelerations, and the attitude in order to generate virtual accelerometer and gyroscope readings. And these are being fed to the flight control computer, as well as the attitude commands and the true state vector. So inside this block, this is the heartbeat check, which measures the communication delay, as we discussed earlier. And the inputs to the PICSOC, as well as the flags that are defined in the initialization script, come into this block. And here we just create a vector signal that can be sent over a serial connection. This block is a variant subsystem which switches between the physical PICSOC connection and the emulated PICSOC. We'll look into it in just a second. And then again, the serial data, which is a vector signal, comes into this block where we just convert it into a bus signal for ease of use. So taking a look into this block, like I said, variant subsystem. So if we enable the PICSOC, we have a packet input and a packet output blocks, and this is what is in charge of sending data to and from the PICSOC. If we disable the PICSOC, then the entire functionality will be emulated directly in the simulation. So this block right here, that's the exact same block that's being flashed onto the PICSOC, and so it operates exactly the same. It receives the same inputs, operates at the same frequency of 100 Hertz, and we even add the delays here in the input and output to mimic the delays that would be apparent from the serial communication. So the data that's coming from the PICSOC is being sent to the servos block. So if we're using the real servos, we actually don't need the information from the PICSOC. Instead, we're just measuring the encoders, measuring the servos with the encoders directly. And if we're not using physical servos, then we do take the servo commands from the PICSOC and passing them through the transfer function for the servos. Okay, and now so we have the fin deflections, and so these go into the nonlinear flight dynamic model. So the main part of this block is the GRM airframe block, and this is the work of Thomas Lausenhammer from TUM, the team in Germany. And this is a very highly detailed and sophisticated nonlinear flight dynamic model block. It takes into account everything from fin deflections to uncertainties, environment variables, and much, much more. So all we need to do is translate the fin deflections into something that this block can understand. Also, we need to give it environment variables. and then we can extract the states that are relevant to us. And we can also stop the simulation at a predetermined case. For example, we can say that we want to stop the simulation once we are at the apogee. So we define this here. And this block only gets enabled after the calibration process for the flight table is complete. So speaking of the flight table, so it receives the true state vector of the missile, and specifically what it takes in is the attitude of the missile. So if we're using the flight table, what happens is there's a three-stage process when we start the simulation. First, we need to calibrate the flight table, so we spin each gimbal by 360 degrees to find the zero indexes, and we use them to convert the encoder's relative angle into an absolute angle. Once we have those, we set the gimbals to move to their initial position so that the flight table is ready for stage 3 when it starts tracking the attitude of the missile. And this block translates the attitude from the flight dynamic model into the 3 gimbal angles, alpha, beta, and gamma, which track this attitude. If the flight table is disabled, we're immediately setting the flight table ready flag to true, but we are still converting the attitude of the missile into the 3 gimbal angles. This is so that the user can try different initial positions of the flight table to make sure that he's avoiding gimbal lock before turning on the flight table. Okay, and the last block is the flight gear simulator block. This is mainly a nice to have, but visualizing what the missile does using simulating scopes is quite difficult. And so it's nice to have a 3D animation. So Flight Gear Simulator is a third-party flight simulator that has a convenient interface with Simulink. So we supply it with the position and the attitude of the missile every simulation step, and it draws it in a 3D environment, which is very easy to visualize and get an understanding of what the missile is doing. The only drawback is that this functionality is only available in the offline simulation and not in the hybrid simulation. Okay, now I want to show a quick demo. So the scenario we're going to be running, we're going to be running the same scenario twice, once in offline mode and once in hybrid mode. In hybrid mode, we're enabling almost everything. So the PICSOC is enabled, the gyros are being measured, and the servos and encoder assemblies is enabled, and so is the flight table. The only thing that is not enabled, so to speak, is the inertial navigation system, and this is just because it's not yet complete. It's the work of another master student to be completed in the near future. And so for now, we're just going to be using the true state vector from the flight dynamic model directly. So the scenario is as follows. We're going to be following a ballistic trajectory, starting with a launch angle of 70 degrees. The simulation is going to start right at launch and end once the missile hits the ground. So there's no recovery section, in this scenario. So no parachute, and we're only controlling the roll angle. So the rest is uncontrolled, and the roll angle we're giving it just a sort of half sine wave shape, just to make sure that we can track some attitude command. Okay, so here's a video of the hybrid simulation. So first thing that's going to happen is the flight table is going to do the calibration process. So that's a 360 degrees rotation for each gimbal. And now it's moving to its initial position. And now it's tracking the attitude of the missile. Here you see the roll command. Now the servos are moving, but because they're moving only a fraction of a degree, it's hard to see in this video. Okay, now the missile is close to ground, and the simulation is finished here. Okay. Okay, so now we're going to discuss the results. So for the scenario we just tested, we are not so much concerned about the performance of the missile. What we are more concerned with is how similar the hybrid simulation is to the offline simulation. And so we can see that if we're plotting the trajectory of the missile in the XZ plane, the two are quite similar. However, in the XY plane, there is a divergence in the Y-axis. We're going to be explaining why in just a minute. We can also show the attitude of the missile. So this right here, this is the command. And so again, the hybrid and offline simulation results are very similar for roll and pitch. However, for yaw, again, there's quite a bit of difference, up to almost 3 degrees towards the end of the simulation. So the reason for these differences are in the servos. So in the offline simulation, the servos are ideal, so to speak. And because we're only controlling the roll angle, then every servo gets an identical command. And so this way, the servos only generate a pure rolling moment on the missile. Now, in the lab, when we're enabling the servos in hybrid mode, they're not ideal. And in fact, even though they all receive the same input signal, the actual deflection can vary by up to even 1 degree between the servos. And so what this means is that we're not generating just a pure rolling moment, but also some pitching and yawing moments. And so this is what causes the missile to develop some yaw angle. And so, of course, the missile is going to be flying having some velocity in the Y direction. We also want to make sure that the virtual IMU is doing a good job at virtualizing the accelerations and angular rates. We don't have what to compare the virtual accelerometers to, but we do have the physical gyros to compare to the virtual gyros. So this is what we see here. And we see that they are almost one-on-one, where the only difference between the virtual and physical gyros are the noise characteristics. And this can be something to be added later to the virtual IMU. But other than that, it's doing a pretty good job at emulating an IMU. Okay, so that's pretty much it. Now we're going to just give a quick summary. So we have a working testbed hardware-in-the-loop simulation in the lab that will allow us to validate GNC algorithms. So I have the PICSOC, which is a flight control computer, which I designed a custom software for it. I also emulated it for the offline simulation, measured the communication delays and their effect. The virtual IMU was also created, and a hybrid IMU was implemented on the PICSOC that can switch between either using the virtual accelerometer and physical gyros, or just using the full virtual IMU. The servos, we identified their transfer function and designed a custom assembly to measure them with encoders. The flight table, we also identified the transfer functions for them. I developed control algorithms for them and dealt with the problem of gimbal lock. And of course, the actual full hybrid simulation that I created runs in real time and integrates this hardware with the mathematical models for the flight dynamic model. So that's pretty much it. Just some future suggestions for improvement. Like I said, the communication delay between the PICSOC and the simulation computer is quite large. And so it's quite important to try to find a way to minimize this delay, either by experimenting with different communication protocols, or maybe even using an entirely different flight control computer. Also, the servos, so the fins in the final missile, once they're in flight, they're going to experience some loads due to the aerodynamic forces, which can affect the transient response. So it could be useful to generate these loads on the servos in the lab as well, and also model their non-linear dynamics rather than just the linear transfer functions to have a more accurate representation of the servos. Also, the IMU noise characteristics can be identified and added to the virtual IMU. And lastly, of course, we can add more hardware to the loop, such as, for example, the GPS simulator or a seeker later down the line. So that's the end of my presentation. Thank you for listening. And if you have any questions, I would be happy to answer them.
Thank you, Guy, for your talk. And we have some time for questions.
Can I ask a question?
Of course.
Go ahead, man.
So aerodynamics was part of the model, because I missed, I didn't see any mention of the aerodynamics of the missile itself.
Yes, so the flight dynamic model, like I said, that's been the work of Thomas Lausenhammer from TUM. So his block of the nonlinear flight dynamics includes everything, including the aerodynamics. And these are just implemented as a block in the simulation.
So how did you simulate the effect of the servo? I mean, of the fin deflections on the missile motion if you don't have any aerodynamic?
Sorry, I'm not sure I understand. 1 second.
You simulated you simulated you commanded a servo motion.
Yes.
At least for the roll, to control the roll. So
Yeah.
how do you know what is the effect of that roll of the fin deflection on the roll position if you don't have any aerodynamic model?
We do have an aerodynamic model. It's part of the nonlinear simulation. So the fin deflections are measured and they're sent to the nonlinear flight dynamic model, which includes the aerodynamics and.
That was my question. Where is it? Okay, right. Okay. So so did it also include the altitude of the missile?
Yes.
Okay, because what is of course interesting is if you see any variations in response from for different altitudes. This is the only reason why you need an autopilot, because you have different responses at different altitudes and also different velocities.
Right. So the autopilot that we're using was actually created by Anne Kitzmiller. So she's in charge of the autopilot controller, and there is in fact a gain scheduling process in there, which takes into account the different flight conditions. Excuse me.
Okay. Okay. Thank you.
Any more questions?
If I may, Guy, very nice presentation. On slide, I think 29 and 20 and 30, where you talk about the controllers of the flight table. Yeah, exactly those, if you can make them large. Full screen, thank you. Here it seems like you're only measuring rates and your position control is like an integrator on the rates. And in the next slide, if you may, it seems like you are measuring only the attitude and you're in the feedback, the washout filter or whatever you have, it's like you're taking a derivative of the encoder. So firstly, well, this S in the numerator, it's like an approximation of a differentiator. So first one, which one is it? Do you assume you're measuring only rates or you're measuring only attitude? And of course, the result, the consequence is, do you differentiate or do you integrate, or at least approximately, which is of course prone to noise difficulties. Like if you integrate, you could have drift, and if you differentiate, we know what differentiation of noise does. So which one is it?
So to clarify, what we see here, this is just the roll autopilot, just a general block diagram for the roll autopilot, just to explain the effects of the flight table. Now this diagram, this is the actual control loop for the gimbal itself. And so we are measuring, we only have an encoder, an optical encoder. And so we're only measuring the angular position of the gimbal. And yes, so what we're doing is we're differentiating this signal to get the angular rate of the gimbal for the inner loop. And this was tested, and the noise that's added due to differentiation doesn't have too big of an effect, and the system is still working well.
So this Polet 100 was just, you just guessed it that it works okay, or is it based on the noise characteristics that you expect, or besides also the encoder? I think it's discrete, right? So you sort of like, so it's like could be very jumpy. I don't know.
Right. So when testing this, I also had a separate simulation, an offline simulation for the flight table, which included everything from saturation blocks to quantizer blocks, etc. And so I have an offline sort of version of the flight table, which I could test against. And yes, you're right. We're using a differentiator to differentiate the encoder measurements. And in this case, a pole at -100. This low pass filter was found to work quite well.
Actually, no. Hold on. This is a high pass because of the S at the origin. If anything, it's a high pass. Yeah,
it's a differentiator, and then we.
Well, it's a high pass. It goes up and then straightens out. So it's not a low pass. Okay. Okay, thank you. And just another thing, in the simulation, it seems like the missile is in a roll angle all the time, or was I confused by the video you've shown? I mean the video, not the. Yeah, here it seems like the inner gimbal is rolled, right? The most inner gimbal is the roll angle, right?
Yes, you're right.
It seems like it was rolled all the time by, I don't know, maybe 20 degrees or something. Which
right. So this is actually the pigsock is mounted right now. The picture is not very high quality, but right now it's actually let's say with a roll angle of 0. It's just that the way that the pigsock attaches to the innermost frame is with a bracket. So maybe I'll have a better picture over here, actually. So this is the innermost gimbal, and there's a bracket that goes from the front to the back. And so this entire pigsock is sort of on an angle.
Okay. Yeah. So when the pigsock is level, the inner gimbal is at, I don't know, 20 degrees or something.
Yes, but also it doesn't actually matter because we're only measuring rates. And so it doesn't actually, well,
you're trying to emulate the attitude of the missile, so it is important. But the missile is rotated a little bit relative to the gimbals. Okay, that's fine.
Yeah.
Thank you.
Any more questions?
No questions for Guy? So